Today I will talk about the progress that we have made with the Intel Heracles platform that graduated from a federal program called DeepRive, and where we are with homomorphic encryption. The work took a village, thanks to the larger team at Intel, Microsoft, Seoul National University, Shia Levy, and collaborators in the community. And of course, please send feedback for anything you would like to dig in more. So first of all, let's talk about encrypted data processing. What do we do today when we encrypt the data? We encrypt the data when we temporarily do not use data. And what that means is that we encrypt object, application, secret, virtual machine. We even encrypt the full memory. But in any case, data is not encrypted during computation, potentially leaving it vulnerable to attacks. With techniques for processing encrypted data, what we complete is this part of the pie, and in particular with fully homomorphic encryption or FHE, data stays encrypted during computation, which means that it stays always encrypted when processing embodiment processes it in its registers or temporarily store it in its cache memory and all the way up to the mass memory in the memory hierarchy. And it's a big deal because it completes the pie of data encryption, and at the same time, it addresses concerns of data privacy regulation that primarily mandate that data stays encrypted, but they don't tell you with what technology. And how can you do that? Well, the idea here is that if in the real world, for example, you have a set of integers, we work with numbers and we process numbers, right? You can have a map that from the real world to something that we call in homomorphic world, exemplified on this slide with a set of butterflies. And if you do have an algebraic structure that allows you to compute arbitrary functions of arbitrary complexity in the real world, and homomorphism basically keeps this algebraic structure, and it allows you to do all the computation in the homomorphic world without interactions with the real world, and the only interactions basically happens in the beginning when you do the transformation, and at the end when you revert the result back. Okay. It turns out that homomorphisms are relatively easy, and probably the only way we know how to do homomorphism is to use real over affine functions, linear over affine functions. And if this homomorphism basically is an encryption function, so you understand how this is going to work. So the first thing is something that everyone knows. When you convert the input into something that is encrypted, basically you have that these encrypted blobs are indistinguishable from each other. And that's the part of encryption that covers confidentiality. But the part of encryption that covers homomorphism, in this case, we talk about privacy homomorphism, is that now you can process on this encrypted data, and more importantly, the output is indistinguishable from the input. So here is where confidentiality invades privacy, and more importantly, it protects against unintended consequences of data processing. Okay. And so what that buys to us is that I already talked about data is always encrypted. The data owner keeps ownership of privacy of its data, but also privacy of the results of the computation. And data is processed, but actually never shared in the clear. The data custodian, that is the processor, right, so to speak, whoever does computation of the data, reduces its risk of third-party data leakage. A, due to data breaches, this is the gray area where security and privacy overlap, and B, unintended consequence of data processing, which is something very new related to data privacy. What can you do if you can process encrypted data? A lot of useful things. You can do private query, privacy-protected analytics, statistics, artificial intelligence, and more importantly, secure data transfer across jurisdiction border. And there are cases where encrypted data processing is basically really a unique tool to use, and the one case is the secure oblivious query, where typically in an information system, the data is relied to an infrastructure. And if this infrastructure is sufficiently deep, meaning that the entity that queries is very, very far, geographically even, from the entity that receives and processes the query, there is the problem that the results of the query can be leaked throughout the infrastructure at any point in time. But with homomorphic encryption, this does not happen ever, because the data is never decrypted. And therefore, if there is a leakage, the leakage is actually can only have happened at the site where the query was initiated. Okay, this is a property that no other security technology can give to you, and homomorphic encryption is particularly unique to solve data use cases like these and others. I will not comment on the other frames because I have them later. But what happened? Homomorphic encryption is still not widely adopted in spite its beauty. It's actually quite a beauty, but it's a beauty that is very hard to harness. The concept of privacy homomorphism existed for about 30 years until the first mathematical object was brought to life in 2009. And at that time, technologists basically said, I will not see this happening in my lifetime. And sure enough, 15 years later, we are actually bringing it to reality. And it went through phases, so to speak. The homomorphic encryption methods, basically starting from 2016, there were several candidates, not too many, but several, but 4 basically are emerging to be the stable candidates. There has been a lot of proof of concepts in the genomic space in particular, but also basically in set operations and in the finance space. But the point is that the overhead of homomorphic encryption is still very cumbersome, that when you actually want to do something useful, it's hard to move from very, very specific and niche use cases. In 2021, the DARPA DeepRight program decided to throw transistors at the problem and say, look, we have gotten the bottom line that the algorithmics doesn't gonna get any better, but we understand what are the algorithms and we can build the hardware for it. And so thanks to the federal government program, we put together basically the first platform, and the program is putting together the first set of platforms that are really designed for homomorphic encryption. And there have been also various tipping points in addition to the DARPA DeepRight program, and most notably, the Edge Password Monitor Services was the first very example where a company like Microsoft, who worshipped homomorphic encryption for nearly a decade, put it at work in their own product. It's a big deal. It's like eat your own dog food. And then there are examples such as the credit system in South Korea, which is admittedly the only public example where you are processing data that are publicly available, right? And the results of this process is not only is more efficient than doing things manually, but also it helps society, because actually you can identify people that receives a pension and are eligible to a credit boost, okay? The standards body ISO-IEC, we heavily influenced that starts basically standards on homomorphic encryption, and it's progressing at the speed of standards body bureaucracy. And then the DARPA DeepRight program is bringing the technology. The other part of it is that today, past 2021, we are seeing words like privacy enhancing technologies and homomorphic encryption in particular coming in all executive order. This is something that's very close to us in the United States. And the point is that while all these executive orders doesn't seem necessarily to have a common strategy, but the words appear, so that's the first thing. And the second thing is that homomorphic encryption seems to be a technology that draws a line across this executive order. It's a real zero trust technology for what concerns data protection, and it enables basically aspects of security and trustworthiness in development and deployment of artificial intelligence. In my organization, which is worldwide distributed, we have 3 pillars of execution. So the first is technology excellence and technology innovation, and that's what I will present today. The second is leading academic research. The third is actually influencing international standard. And even though I sit basically in a research workshop, so to speak, I care that the technology basically develop together with these three pillars such that it can be transferred to effectively erode. So what are we doing with homomorphic encryption? First of all, let's understanding the complexity and why it's not used that, why it's so cumbersome. So modern homomorphic encryption is homomorphic encryption in polynomial ring. And as it's illustrated in this box, input clear text data is actually encrypted into a tuple of polynomials, exemplified basically by these vectors that are components of encrypted A. And because it's an encryption technology, you would believe that it's parameterized to something. And definitely there is the length of these vectors that is telling you the security that you can put in place when you instantiate homomorphic encryption. And then there is the length of the coefficients of this vector, the bit width, that is telling you how complex of a function an instantiation of homomorphic encryption can handle in order to complete the computation and decrypt correctly. And the encryption function is a linear affine function, and it's non-deterministic, which means that given the key and the message, it does a linear operation on the key and the message, and it adds noise. That's the affine part. And what that gives to you is that you can add and multiply ciphertext securely, and it's very easy to show that if you add the two ciphertext, the addition of the two ciphertext is a component of the results of this addition, as well as for the multiplication. But because you are adding this noise into it, you need to manage it, because the majority of these operations are on finite arithmetic overall. And if you wrap around the boundary of this finite arithmetic, because the noise accumulates and grows too much, you risk not to decrypt correctly. And so you need to introduce noise management in addition to the arithmetic operation that you would find in the clear text in order to make homomorphic encryption to work. The community has worked a lot on security guidelines. The latest version primarily influenced and led by my organization. And these parameters are related to each other. Just to give you a little bit more sense, the circuit depth, which is the critical path of multiplication, is what basically helps you determine how large the coefficient bit width is. And if your circuit is much larger, right, you get larger parameters. And that is what is called the leveled homomorphic encryption, which is the majority of the practices that we see today. What is the downside of this is that the larger is the function, the larger is the parameters, and the larger are the parameters, the uglier is the encrypted clear text, which means more overhead. So what you can do is that you can cope with the noise accumulation and keep the parameters bounded by using the noise refresh operation. And the side of this box tells you that those are as complex probably as the function that you are calculating. But you can do that, and sometimes for very big function and to process function of arbitrary complexity, arbitrary function of arbitrary complexity, that's what you would do. You refresh the noise in the middle, you select the parameters that are mainly associated to the complexity of bootstrapping, which is effectively evaluation of the decryption circuit, homomorphic evaluation of the decryption circuit, and you can basically have this trade-off. The points on this line are clearly not in scale, so there may be a difference of tens of thousands elements in these vectors to ensure that homomorphic encryption is instantiated securely. And so when all of this is done, if I want to do basically a clear text multiplication for reasonable parameters, there are two things that happen. There is a blow up in the data size, and there is also basically a blow up in the amount of computation that you have to do on CPU. And if you actually do use cases, you can see that the majority of the operation, those are use cases that actually we do have in a house. You can do very complex things with homomorphic encryption today, actually. The majority of the time is spent within ciphertext management operations, which means that not only you need to make your homomorphic arithmetic fast, but it has to be very, very fast in order to make the algorithms that do ciphertext management operations fast. So we built, Heracles, which is a new type of computer architecture, fundamentally based on the concept that anything that you have in the clear text is encoded into some polynomials of finite degree and finite coefficients. So we introduce a new data type which embeds polynomial ring arithmetic. And it's a new type of computer architectures because the majority of this computer architecture allows you very fast simultaneous interactions between the coefficients in the compute, and therefore it has a very efficient network of relay between the functional units, and the memory is distributed outside. It has a very large degree of parallelism, and it takes advantage that homomorphic encryption programs are not ordinary programs, but they can be scheduled offline optimally. The first instance of this embodiment is a card, which is going to be PCI attached to a server. It doesn't come only with the hardware, it comes only with software, which is a special software to bridge the gap with the traditional programming and homomorphic encryption programming. And the platform itself embeds the state-of-the-art homomorphic encryption methods, as well as the state-of-the-art algorithms and new variants that came out in the past few years to address basically the need to target these new, very highly parallel and specialized architectures. So just to give you an example on what this buys to you, if you look at the number of instructions basically that you do on CPU, those are the basic tools that the platform comes with, and then there is a front-end compiler on one side, but with the basic tools you can program it. The homomorphic encryption operation on CPU, that requires millions, if not billions, of CPU instructions. But the fact that we embed basically the instruction set architecture of Heracles in polynomial ring arithmetic, you can see that the number of polynomial ring instructions that you do is much smaller. Therefore, if you can make this polynomial operation very, very fast, you understand where the speed up is going to come. And of course, we have all kinds of optimizations that we do in our toolchain. Today, I have to admit, many of these things are still done partially manually. Okay. But they are being automated as we talk. So what does this buy to us? Well, it buys to us that Heracles gives you 3 to 4 orders of magnitude speed up compared to CPU in performing full homomorphic encryption operations. Then the throughput of basically clear text operations compared to that can be carried through ciphertext basically can be in the gigaops, and it all depends basically on your ability to encode the clear text data within ciphertext, and that is a function of the cleverness on how you architect your workloads, but also the capacity that the homomorphic encryption method brings to you and allow you to do. What that means in practice is that if we look at some workloads that have been worshipped in the homomorphic encryption community for a long time, there is a variable speed up that is very, very misleading. Again, it depends on the capacity of the schema to pack SIMD data, but the overhead, okay, compared to clear text, it's not the millions of thousands anymore. It's 10 to 100 at the point in time that I took this snapshot, which was over a year ago, and it's 1 to 10 now. Okay, and just to give you an example, this is what the talk was going to. As soon as you get into the 10th of milliseconds, and hundreds of milliseconds, but not beyond that, you actually enter in the realm of interactive to real-time performance, okay, which was something that was important. In summary, there is this platform that brings software and SDK, and the first instance of this embodiment is a PCIe card. We tape it in, the silicon is coming back, the first silicon is coming back in the fall. The SDK, don't quote me on this, should be already out in the open source, at least the first version of it. But we have a phased approach to release basically SDK for its consumption, cryptographer, library, and compiler writers, and then FHE application developer, and then general things. We have an early engagement program starting next quarter. Get in touch with us for trying out this stuff, but also if you are interested in competing for a source of funding that can further enhance common research, please come and work with us. We are very eager to do that. I think I'm running out of time, but I want to conclude with 2 slides. We have also contributed to a huge chunk of literature. As you can see, selected publication, and we influence international standards, both national standards bodies, as well as we have a seat everywhere in the de facto standards. We want to make this happen. Encryption requires, I'm going to skip this slide. So we talked about the fully homomorphic encryption, elevates the bar of confidentiality in existing security solution. There is one challenge that we definitely will overcome. The pony trick is out. Performance is not an issue anymore. Business opportunities are receiving a lot of attention. According to my business developer, this is the technology that has received more interest than any other security technology in the past, and based on the discussion that we have had. And as we have seen, it's a technology that can draw a line across anything that we are seeing in the executive orders from the White House. And usability is the next big challenge, okay, which means many things. Program translations from clear text to homomorphic encryption, integration with existing security mechanisms, and integration with the data processing pipeline. So because homomorphic encryption was so cumbersome, okay, the application domain is largely unexplored. It's a niche thing today. But now that we cut through the performance problem, it's time to explore the application domain, but also to integrate it. It's not done yet. Okay, but the main stumbling block that has been solved. With this, I'm happy to take questions, and I hope I was kind of on time.
You're on time, and I think let us hold the questions, and we'll go on to the next speaker, which is Abel Coe from Northwestern, who will give an idea of an application of homomorphic encryption. So, Abel?
Yeah, let me just pull my slides up. And while I'm pulling them up, so thank you, Jonathan, for the opportunity. Ro, that was a great talk. I was really excited to see how far you've come along with improving your performance. One disclaimer: I am not that kind of doctor. I do not have a PhD that was listed on the announcement. I'm actually just a regular doctor. So, but I'm going to describe to you the last 15 years of trying to build a real-world laboratory for deployment of privacy-enhancing technologies. And I think this is complementary because my focus is going to be on privacy-preserving record linkage and secure multi-party computing, both of which we've deployed in real-world hospital settings. So I have one disclaimer, or rather one disclosure. I'm an advisor to Datavant through acquisition of a company we spun out quite a few years ago. So let me just see if I can move stuff around my screen so I can see what I'm actually presenting. Okay, so again, I'm going to focus today on privacy-preserving record linkage, real-world applications, and secure multi-party computing. But what I really want to focus on is that a lot of these privacy-enhancing technologies are oftentimes stuck in laboratories. When you try to go to deploy them in the real world, you really have to focus on 3 other Ps. And what we've learned is that you have to really understand the fundamental problem you're trying to solve, whether it be a scientific or organizational or institutional problems. You really have to be pragmatic because a lot of these theoretical constructs, they don't translate well into the real world. And then you have to understand local politics, because if you don't understand those, a lot of technologies are really about change management. If you don't acknowledge those, then you won't really go very far in the real world, despite how good the technology is. So I'll give you a couple examples. So the first problem we were trying to solve that led us to PPRL was way back in the day. We were trying to understand what is the prevalence of diabetes scattered across Chicago. And at that time, there's no health information exchange. We were working on a genomics project. And we realized that you've got these different catchments of hospitals all around the city. But if you really want to get a prevalence rate across the city, you need to combine all those different overlapping sets. And then if you could take out the duplicates, you would get a much more true example of what the prevalence rate for this condition is. In this case, it was diabetes. So that was the scientific problem we were trying to solve for in preparation for a proposal. So that led us to, think about how we're going to do that. Realized we couldn't get data pooled together from multiple institutions. And so we asked a really kind of absurd question, which was that we tried to find all the institutions in town, academic institutions. We asked them to say, okay, look, we're trying to solve this problem. Everyone will benefit. There's going to be insights from this pool of data. So can you all give us a one-time cut of a big swath of your data? And anybody who knows competitive environments realize that's an absurd request. And so that led us to this realization that we would never get that unless we found a way to provide reassurance to all the parties that their data would be fully anonymized and protected. And so that led us to develop our initial cut of privacy-preserving record linkage. So we did that, working with students, teams from across the institutions initially, and then we sort of hardened the software after that. What we realized was that when we pulled those data together across multiple institutions, we got a very different rate of diabetes combined than if you measured each one alone. Quite a lot of difference, about 24% reduction in the counts or prevalence rates of diabetes when you combine them together. That led us to improve the software. And so the big trick here was to take all the different inputs that would go into this hashing algorithm and then really make sense of it, clean it up, standardize it in ways through a series of steps, and then create multiple different tokens or hashed versions of an individual. Because there's missing data in one place, so they changed the name over here. And so what we did is we essentially created like 20, 30 versions of a person in the encrypted space. And those became the tokens by which we could match people for record linkage. And that ended up becoming a company, and then eventually got acquired by Dataman, hence this disclosure. But one of the things that we discovered along the way, this is the pragmatic part, is that the HIPAA regulations that govern, use of identifiable data or de-identified data stipulate that you can only do this if you, in essence, have set up an honest broker, because you really can't share even the key tokens with other parties who happen to also have access to that raw initial identifiable information. And so we needed to create an honest broker. So, 2-3 years along the lines of developing the technology, in parallel, a number of us actually pooled together, and recognizing there wasn't a neutral party in Chicago, we created a honest broker. So we created a 501c3 called Mariah. It was a good name at the time. And that has become the honest data broker for a lot of our PPRL projects in Chicago. Again, it serves multiple different types of constituents, academic institutions, state government, et cetera. And it's sort of become its own sustainable organization over the years, again, as a 501c3 with a independent board. So all of us volunteer our time. None of us take any salary from this honest broker function. And we have sort of rotating membership of board folks from around the city of Chicago, all who are really committed to public health or the wider good. So all volunteer sort of board. And we've engaged in a number of projects around hepatitis C. I think this might be NIDA, some opioid treatment work. Obviously, this work I'll describe to you shortly, and work on tracking infections throughout the region and for the state of Illinois and for the city of Chicago. So what that led us then is to sort of put even more wrappers around our nascent data sharing efforts. We created this thing called Capricorn. And what that has at the hub is this honest broker function of Mariah, which serves to sort of deduplicate individuals' identities across all the different institutions. And we've also standardized all the data across all the different systems into these standard common data models on the right. And then how it works today is that a person can go ahead and ask questions. A query is sent out to all the sites, returns back standard query results. Mariah integrates them together using PPRL if necessary for deduplication of records, returns an answer back to the client. And so that's created this network, the Chicago Area Patient Centered Outcomes Research Network. One of the big benefits of this network is it creates a living laboratory for some of these technologies. because we have governance, we have an IRB shared across all the institutions, we have legal agreements that allows us to go ahead and do all the way up to identifiable information sharing if needs be with appropriate approvals. And that's important because you want to verify the results from some of these privacy enhancing technologies. It's nice to run scientific experiments where you can see, did it really do what you think it said it was going to do? So this is a really important sort of pragmatic infrastructure you have to wrap around these technologies to enable them to be tested in the real world settings. So one thing that sort of told us this we're onto something is that we started then getting asked real world questions that people wanted us to answer for them. And so, quite a few years back, the VAs, I think you may have recalled, there was this concern about veterans seeking care outside the VA system and were they providing the right services for veterans. And so we were asked this question about how many veterans in Chicago receive care outside the VA system. And so we were able to basically use PPRL to link VA records with records from the non-VA institutions and come up with an answer for them. And so that answer was that basically about 34% of veterans, this is probably an undercount, in Chicago receive care at some non-VA facility over the course of a year. And then we were able to break down the diagnoses and see that, in fact, it made sense. A lot of veterans manage their chronic diseases, some of their substance use issues within the VA, mental health issues, but then they did a lot of their specialty care outside the VA. So this is a very useful answer to some of the constituents in our group. The practical and politics part of this is that we already had a neutral, honest broker, but we had to go through an approval process to get this software certified through the VA local and national. That took about a year. And we also had to have one of our team members actually employed as 08th employee within the VA to actually deploy the software. So there's a lot of things that additional steps you have to take to make this type of technology work. More recently, we were asked about homelessness. And so a lot of the health system leaders came together for a meeting, and we were trying to think of what are problems that all of us face. And homelessness is a problem, not just in Chicago, a lot of urban settings, but they asked the question of us, can you answer the question if providing housing, because they were contemplating supporting housing, does housing the homeless help reduce the burden on our health systems? Would it reduce the number of people coming into emergency departments? And then this is work that was led by Bill Trick and Fred Rockman from Alliance Chicago, Bill from county. And what they showed by linking both the homeless management information system data with clinical records was that if you give people stable housing, yes, it reduces the use of the emergency department, reduces hospitalizations, and they use ambulatory visits more appropriately or outpatient care more appropriately. The other interesting part is, again, breaking down by diagnosis, is you can see that if you give stable housing, some of the problems that were high on the list, things like foot pain, where people have they're out in the exposed to the elements, it goes from being very high order concern to a much lower order concern over time. And so you can see how that housing also has additional benefits to the individual as well. Now, PPRL is just one tool in a toolkit. And so, maybe 8 years ago, we came to the realization that there's limitations. People still are going to compete. You still need to have an honest broker. What if people don't trust the honest broker? And there's other types of privacy institutions are concerned about, like their business practices and the requirement for all these legal agreements. And it's really expensive. It's hard to add on new people into this network we have. And so that led us to start exploring secure multi-party computation. And we were lucky that Jenny Rogers is in computer science at Evanston. Xiao Wang was recruited from Maryland. He had already developed something called the EMP toolkit, multi-party computing toolkit, an open source sort of version of the multi-party computing. And so we partnered with them. We got some initial NSF funding, a career award for Jenny. And then she's been working with us now for, I think she's been 9 years now, to build out this real world application of MPC. And the result is this project called VaultDB, which is, like the real world. It's a data sharing platform for people who don't trust each other, which I would argue is most of the world today. And so, it really gives us an additional layer of protection, and more importantly, we think can remove the need for an honest broker. And so, again, there's a lot of practical sort of things you have to go through to make this work. So right now we have an honest broker. Our goal is to remove the honest broker from the system. And the current MPC protocol we use, the VaultDB workflow, looks like this, where essentially a question is asked. We send out the protocol out to the various sites who can run the query locally against standard common data models. The computation is run locally. We try as much as possible from a computational efficiency standpoint to offload the computation to local, unencrypted, and then encrypt. And then the secret shares are sent back to be joined together for an answer for the client. We put out a paper just, I think, 2 years ago, and this was a summary table. So one thing that we've come to realize when writing these queries, you do have to think of it a little bit differently. You have to almost start from the output table first and work backwards, because what you can then do is break down each individual cell within the table into smaller computations. And that has allowed us to be much more efficient in running these MPC protocols across the sites in Chicago. Right now, it's currently funded by DARPA. We've partnered up with, I think, Secure Software Technologies, a firm run by Steve Liu and Raphael Ostrovsky. And we are now sending this work, and so we actually have it installed in 5 different institutions, and we're actually using it for public health purposes as part of a project with Chicago Department of Public Health as well. So this is real live data, and it actually seems to scale reasonably well as long as you off-put or push off some of the computation to local sort of computes first before secret sharing. That seems to run pretty efficiently. I'll just have a few quick more slides. One other real world problem we're facing is that we've been asked about climate change issues. And so we are in the process now of actually integrating in environmental data and weather data on top of our clinical data. This is initial funding from our local Buffett Institute in a project called Diffusing Disasters. For this, we use, people don't always think about this, but geocoding, but distributed kind of like our encryption tools. We can also push out a geocoding tool to do local geocoding with all the reference files. This is a tool developed by Cole Brokamp at Cincinnati Children's. And we've been able to contribute to that community and add very fine-grained environmental and climate data into these reference files that local sites can download, so they can generate local instances of their patients' exposure to heat or environmental data at 1 kilometer squared exposures, because linkage can be done at the person level and also at the place level. This is place level linkage in a way that is privacy enhanced. So this is work that we've been sort of also working on in parallel. One last plug, if people are really interested in record linkage, we're actually hosting an international conference for the first time in the US in Chicago in December of this year. It's called the International Population Data Linkage Network Conference. I'll put a link in the chat in a second. But it turns out there's a whole international community working on both all kinds of data linkage, not only PPRL, but other kinds of linkage, and really demonstrating some really exciting real world uses. So I think I stayed on time. So with that, I will stop and also be happy to take questions. Thanks.
We'll hold questions, and Lee Xiong has joined, so he will present now. And then we'll open up for discussion. So 20 minutes.
Let me see if I can.
Thank you, Jonathan. Can everybody hear?
Yes.
Great. Thank you. And sorry, I somehow had 11:30 on my calendar. All right. Thank you for the opportunity. So today what I'll do is to present some of our recent work in harnessing decentralized healthcare data with federated learning and personalized differential privacy. So this is joint work with students and collaborators at Emory, UT Health, Yale, including Dr. Xiaoqian Jiang and Dr. Lucila, who have presented in the seminar series before, and also collaborators from Vanderbilt and UVA. And these work are supported by an NIH R1 grant and a NSF SATC Trustworthy Computing Program grant. So just a quick word about my lab. I direct the Assured Information Management and Sharing AIMS lab at Emory University. We work on the pretty much intersection of machine learning, data management, and data privacy and security, particularly privacy enhancing technology, and look at their applications for healthcare and public health. So we've seen a great range of privacy-enhancing technology and their use cases presented in this seminar series, including homomorphic encryption, multi-party secure computation, trusted execution environment, privacy-preserving record linkage, as we have just seen, also federated computation and learning, and also the statistical privacy or differential privacy also got mentioned. There are also other privacy-enhancing technologies such as synthesizing data, and then there are other issues like governance, consent management from the patient's perspective, and also the emerging like machine unlearning, where we already trained machine learning models, but some patients or users have the request to have their data forgotten or removed because of GDPR. So there are also techniques that are dealing with how to do machine unlearning, removing the influence of certain users or individuals from the trained models. There's a chat. Okay. So what I'll do today is to focus on the federated learning aspect, and in particular, combining federated learning with statistical privacy or differential privacy to have more rigorous privacy enhancement in the federated learning scenario. So here's a quick motivation. I guess we're just preaching to the choir, but as we have seen from earlier talk already, again, it's tremendously beneficial to harness the decentralized data that reside in different institutions about our patient data, especially, for example, for rare disease cases or at early stages like a COVID, when every institution only has a small number of cases or patient cases. So it's if we pull this data together and jointly train a model, it will make the model more generalizable, more powerful compared to just using the data alone or local data to train a model. So as Dr. Ko focused more on the queries in his talk, so I'll focus more on the learning part, where the goal is for these institutions to jointly learn a machine learning model for disease treatment or diagnosis and so on, using their data together. But of course, we can't just directly share or pull this data together. So federated learning has becoming a prominent paradigm that allows multiple institutions to jointly train a model without sharing the data, while keeping their data local at each individual site. So in my talk, I'm mostly going to focus on the horizontal setting, which has been mentioned in earlier seminars. This means every patient or every institution would have the same set of features, but a subset of different patients. So for now, I'm just going to assume there's no overlapping of the patients. Every client or every institution or every hospital have a set of patients, and then they all share the same set of features. So their goal is to jointly train a model. And just to have everyone on the same page, the basic or the typical federated learning algorithm involves several steps. So the first step would be the server just sends a randomly initialized global model to all clients. And then each of the client using their local data, their local patient data, to train or update the model. And then they can send this model or model updates to the global server. So this is the key step. They're not sending data to the server. So that's why federated learning has some inherent privacy benefits. They only send the model updates or a model like gradients to the server. And then the server does aggregation. They pull these local models together using some kind of aggregation. And the most commonly used aggregation is just average or weighted average, depending on the size of the data set. They just do a weighted average of the local models, and which becomes a global model. And now the server can share the global model to the individual clients again. And then these clients or hospitals can repeat these steps multiple times through multiple iterations until the model is converged. So this is the typical process for federated learning, which is great. As we have seen, it's very straightforward. And it allows multiple institutions to jointly train a model without directly sharing the data. And of course, besides the inherent privacy benefit, it's not privacy proof, it's not bulletproof. And as we have seen here, the intermediate models that are being shared between the clients and server, they can potentially leak information, or they can be used to infer the original training data. And then the global model can be also used to infer the original training data. So we have seen in earlier seminars, again, there are homomorphic encryption or multi-party computation that can be used in these to ensure the computation is secure, meaning the intermediate exchanges between the clients and server, they can be encrypted so that they can ensure the confidentiality of the exchange information. However, the final global model still has the inference risk. So that's why a lot of times we still need additional privacy enhancement to ensure the inference risk of the final global model is minimal. Or those same type of technique can be used to ensure the intermediate information has minimal inference risk. And typically this technique we are using is called statistical differential privacy or differential privacy. Essentially, what we're doing is to add in some randomization process, either in the data or in the local training process, or in the uploaded model updates, adding some randomization such that we can ensure the intermediate model or the final global model ensures differential privacy. And again, just to make sure everyone is on the same page, differential privacy is a statistical privacy framework that was introduced around 2006 and has been pretty much standardized or become a standard framework now for statistical data analysis for privacy protection. And if we look at the lower left figure, the main idea behind differential privacy is that given any function that we want to perform on a database, and consider or imagine there are two neighboring databases. One database is with your data, and one database is without your data. And if we apply the same function on these two versions of the database, and we get output A and output A prime, and differential privacy essentially requires the output A and A prime are similar or indistinguishable. So that way, we actually have the privacy guarantee for your data, because the adversary would not be able to differentiate whether the output is coming from database A with your data or without your data. So basically, it cannot infer the membership of your data, or whether your data is present or not present in the original training data or in the original database. And the typical way to satisfy differential privacy is adding randomization. And for example, for building machine learning models, this function can be statistical summary, can be machine learning model, can be even synthetic data generation. And in order to satisfy differential privacy in the machine learning scenario, typically the way to do is to add some randomization in the gradient process. So it's called DP-SGD, or DP stochastic gradient descent. Such that we can ensure the model is differentially private. And in the federated learning scenario, this differential privacy can be typically combined with the multi-party secure aggregation, as we have seen earlier, so that we get better trade-off in terms of utility and privacy and efficiency. So this has been, in the community, there has been a lot of work related to federated learning and MPC and so on. So in our work, we are mainly focused on one aspect, which is how can we actually ensure the rights to control the privacy from the institution and from the patient's point of view. This same point has been also brought up in Dr. Lucila's presentation earlier, where she presented the I-consent system, where we want to value the perspectives from the patients and institutions. So in the traditional or standard differential privacy work, and particularly in the existing deployment of differential privacy work, most of these applications just assume the server or whatever the data curator or data custodian would set a uniform privacy protection parameter. So this epsilon is a key parameter of differential privacy, which essentially controls the level of the noise and the level of privacy protection. The lower the epsilon, the more noise that's required, and the better or stronger privacy that's guaranteed. So for example, in Apple's differential privacy deployment, they set epsilon to be 2 to the 16-ish. And for Google's application, they set epsilon to be 2-ish. And then for the 2020 Census Bureau, data release, they use differential privacy for their census 2020. And there they set epsilon to be 19 in one of their white papers. So these, again, this is a kind of a multi-million question, basically how to set this epsilon value and how to ensure the trade-off and how to communicate these epsilon to stakeholders, to our patients, and so on. So this is a very open question. So in our work, we are trying to take a perspective from the patients and institution perspective. Essentially, we want to argue that different institutions, they may have different privacy requirements and policies, and different patients may have different privacies and different privacy preferences and attitudes. They may want to have or make their own choices in terms of how to set the privacy level. And as Lucila mentioned, for example, in her talk, some patients may be willingly, openly consent to have their data directly used, while some patients may have more strict patient privacy preferences. So how do we actually take these into consideration in our federated computing scenario? Those are the main two challenges that we're trying to address in our work. And finally, some patients may have records across multiple institutions. Existing work typically just assume each record belongs one patient, belongs one client or one institution. So do not consider these cross-institution kind of privacy guarantees. So consider these challenges. Our main solution are several-fold. First, we are looking at how to guarantee or how to ensure client-level personalized differential privacy, which means each institution can have a personalized or set their own privacy budget. And second is a record-level personalized DP, which means every patient within each institution can set their own personalized differential privacy. And then finally, how do we ensure cross-institution user-level differential privacy in addition or instead of simply record-level differential privacy that does not provide a rigorous privacy guarantee for each individual patient or each individual user? So I'll just spend a couple of minutes going into each of this very briefly without going into a lot of details. So first is how do we support client-level personalized differential privacy? So I give a very quick example here. Consider we have 4 institutions, and each institution set their own privacy parameter or privacy budget. Right? Client C1 sets their epsilon to be 0.1. This means this is a very strict privacy budget, very strong privacy, and that means when they upload their local models to the server, their model is going to be very noisy. And then in contrast, we have client C4, which has their privacy budget set to epsilon equal to 10. That means they are less strict. So their model uploaded to the server would be less noisy. So now the question is, when the server receives these local models, how does it aggregate these local models into a global model that's less noisy, that takes advantage of these varying privacy parameters or different noise levels of these individual local models? In the baseline approach, federated averaging that's most commonly used for federated learning is going to lead to very noisy models because some of these models are very noisy. And a slightly improved approach is to do weighted averaging, meaning we can give a higher weight to these less noisy models, but then this would lead to bias towards these kind of less noisy models or less noisy institutions, which is also not what we wanted. So essentially, our question is, how do we take advantage or take into consideration of these personalized privacy preferences without biasing this model into the less noisy institutions, and also still take or utilize the noisy models from those strict clients? So our approach essentially is a projection or substrate space-based projection approach. The idea is to utilize these less noisy models and extract the subspace using, for example, principal component analysis, extract the subspace from their model updates. The main motivation or insights behind this is that even though all the models that we're dealing with today, they can be very large, the dimensionality of the models can be large, but the literature has demonstrated that even though these models are large, but the essential information, the most important information still resides in a very, very small subspace. And if we can extract the subspace from these less noisy models, then we can utilize this subspace and then have the private clients or more strict clients to project their model updates into the subspace. So this way we mitigate the noise of these noisy models and extract only this essential information for the aggregation. And in this way, we can enhance the privacy and utility trade-off of the global model. So that's the main idea of this work. In terms of how to take into consideration both noisy models and less noisy models because of their personalized differential privacy requirement. And here, just some quick result. Without going into the details, essentially the main finding is that by doing this projected approach, it outperforms significantly compared to the baseline averaging and the weighted averaging. So that's for the institution level customization or personalization of the privacy. And then if we go down one level, as we mentioned, even within each institution, consider here we have 3 patients. Each patient may have their own privacy budget or privacy preferences. So each of them can set a personalized privacy budget, epsilon 1.1, epsilon 1.2, and epsilon 1.3. So in this case, when we are training the local models, we need to take into consideration this individual personalized differential privacy requirement of the individuals. So our main idea is to use the record level non-uniform sampling. The idea is when we are using these records for doing training, we can do a sampling using a non-uniform probability. So imagine if a user, if a patient's record gets sampled more often, then obviously it will get more exposure. But in contrast, if a record gets sampled less frequently, then the record will have a stronger privacy protection. So to basically satisfy or to achieve these record level personalized differential privacy, we can assign a non-uniform sampling probability for each patient or for each individual user. But the challenge is how can we actually quantify or estimate these personalized non-uniform sampling probability so that at the end, after all these iterations, the accumulated privacy cost can be similar or can be close to their privacy budget so that we don't overspend their privacy budget or we don't underutilize their privacy budget in both ways. So that's why we need a precise quantification of these sampling probability. That's where our mainly proposed solution is. So again, this work was recently is going to appear in this year's CCS conference. So without going into details, I'll just show you some quick result. So we can just look at the second column, which is a heart disease data set, and we can see the orange line again is this record level personalized differential privacy approach. We can see it outperforms other baselines. For example, we can just use the minimum privacy budget of all patients. That's a very naive baseline, or we can drop out some of these users, set a privacy budget, and then drop out those patients who have the privacy budget lower than our threshold. And so these baselines basically do not perform well. So that's for the record level personalized privacy. And finally, we look at this problem where one user or one patient may have their data belong to multiple silos. So here it shows 3 hospitals, and this user may have their data belong to 3 hospitals. So in this case, a simple idea is we can just use typical differential privacy, but scale up the noise. It's like imagine this user record can scale the noise up to the 3 times so that we still have the privacy guarantee, even if the user have data at 3 institutions. But this will obviously lead to poor performance because each user or not all users have their data at all institutions. And another idea is to use group DP notion, where we assume each user has at most K records at K institutions, respectively. But the challenge here is that there are some users who might have more than K records. And then there are also users who have less than K records. So how to set this K so that we can still have rigorous guarantee and also good privacy utility trade-off. So it's a challenge. So in our approach, we basically designed a personalized user-level differential privacy approach that specifically satisfy the user-level differential privacy. It's based on the per user, per institution, or per silo gradient clipping and perturbation approach. So again, I won't go into the detail, but the main problem we are addressing hopefully is clear. Essentially, we are trying to ensure, even in these cases where each user has multiple records at each institution, we still want to guarantee a rigorous privacy and also optimized utility. So here's a, again, very quick illustration comparing our methods with some baseline methods. We can see it will have a better utility and accuracy or privacy trade-off compared to the baseline approaches. So hopefully that gave you some ideas of our current work in the hope of kind of addressing these personalized privacy expectations from both institutions and patients' perspective. So I'll just spend maybe a couple of minutes also briefly tell you one effort that we were involved in last year in terms of organizing a US-UK privacy enhancing technology price challenge that was organized by NSF and NIST. So one of the scenario or for the challenge scenario we organized is using federated learning for pandemic risk prediction. So the scenario is we have multiple institutions or multiple, let's say, regions or counties, and each county has their own contact network of their users. And the contact network basically means each node is a user, and each link means they have a contact over an aggregated time period. And the task is, given this contact network and given some nodes that have infected status, we want to predict or forecast in next time period how many of these users or how many of these nodes will get infected by the infectious disease. And of course, each of the institution or client can use their own contact network to do the risk prediction. But because they have limited data and they have these missing neighbors of some of these users, so the model would not be accurate. The idea is to use federated learning so that they can utilize all of these decentralized contact network or contact information together without directly sharing the data so that they can build more robust, more generalizable models, more accurate models. And for the challenge, there are several criteria. First of all, of course, is privacy protection. And we want both formal privacy security guarantees, such as MPC-based guarantees or differential privacy guarantees. And also for the challenge, we have a red team, which basically designed various attacks trying to infer, for example, whether a node is infected, whether two nodes are in contact, and so on, trying to infer these different varying level of information as a red team attack or evaluation, and see which of the challenge team would be most robust to these attacks. And of course, the second major criteria is the model utility. How does this model work compared to a centralized model, as if we put all the contact network together into a major global contact network, then there we would have a ground truth model. And finally, computational cost is also one criteria. We want the model to be efficient, and also communication-wise, it shouldn't incur a lot of overhead. So, Jonathan, sorry.
I'd like to leave some time for discussion, so.
Yeah, so I'll just finish in 1 minute. Thanks. Okay. So these, I just want to show you, these are the winning solutions. And as you can see, very interestingly, all of them use differential privacy to ensure the inference risk is low of the model. And most of them use homomorphic encryption as a hybrid approach to work with differential privacy so that they can actually have and multi-party computation so that they can actually have a good trade-off in terms of both confidentiality and inference risk and computation efficiency and so on. And also another interesting fact is that if we look at the last column, which is the ML model that are being used, we can see most of them are classic ML models like XGBoost and logistic regression. We don't see many neural network-based deep learning, fancy deep learning models. So again, this just is an interesting insight that if we want to use, for example, MPC, maybe some of those very complex or differential privacy, those complex models may actually have a very high cost in terms of privacy utility trade-off. So sometimes using these classic simpler models may give us overall better trade-off. So I'll leave it there, just some discussion point, and we can probably, I'm sure we will get to some of these as we discuss. Basically, how do we deal with these complex data and models that are particularly in the healthcare domain so that we can have good privacy utility trade-off in this setting? And how do we build better, more seamless hybrid approaches with homomorphic encryption and MPC and differential privacy? How do we consider personalized privacy preferences? And how do we communicate these privacy technology to stakeholders? And how do we make sure other factors are considered, robustness, efficiency, and fairness? I think one of the points, Jonathan, you raised earlier is that when we consider these personalized privacy preferences, do we actually introduce bias into this model because of different patients have different privacy attitude, and then the collected data or used data may have some bias in it? And then also, finally, I think we can avoid these emerging LLMs and pre-training fine-tuning paradigm that are increasingly being used or adopted by the healthcare. So how do these introduce new opportunities and challenges into these settings? So these are all, I think, good points that we can discuss. So with that, I'll conclude. Thank you.
Okay, thanks. Okay, it's open for discussion. I had a couple questions initially to Ro. So, I mean, what's the cost of implementation of homomorphic encryption in terms of the power usage? I mean, there's an article, I think, in either the Washington Post or New York Times saying all of these high tech companies are overwhelming power usage in the United States. And what's the actual what's the actual cost to the actual user, in terms of implementation?
Right. So there are a couple of I think there are multiple aspects to your question, right? So to the actual user is the one that is supplying the data and wants privacy. So from the actual user perspective, the cost is small, right? If nothing else, the interface is going to be the same. What happens behind the interface is slightly different because it's different cryptography, right? But it's independent. The cost to the infrastructure that relays this type of information and also performs the key management, there's a cost there because the key management is different. Now that's the impact. Now there are another two parts to your question. So the first is, what does it take to implement things in homomorphic encryption and integrate within the flows that we have today, right? And once you have all of these working, what is the environmental impact? I think that's the other part of your cost in that. So the translational programs do homomorphic encryption today, even if you have this great hardware, there are only few instances where the translation is kind of seamless and the hardware gives you performance, let's say, for free. Okay, you still need the experts to look at programs and do the right planning and the parameterization and things like that. Again, until now, the niche use is not going to be changed immediately by the hardware. But as development tools and translation tools become more mature, and I want to give an example that is participated by much of the community, which is the homomorphic encryption intermediate representation, by Google, Intel, and others, right? Then the translation problem becomes easier, and that cost of developing and testing is going to go down. Okay. Now, from what concerns the environmental impact, I can give you some kind of in the middle between quantitative and qualitative answer to an extent that I can share this. So this type of accelerators, at least in their first instances, they look like a GPU, but they can actually perform homomorphic encryption very efficiently. From point of view of power consumption, right, of these things, they actually consume about half of a modern GPU. Okay, so there is an impact processing encrypted data. comes with the complexity of encrypted data. Okay. But we are, it's what we have to address, very sensitive use cases. And of course, another thing I think that Kurt was pointing out in the comment that I just shown up is that it's not that you implement homomorphic encryption and you wipe out all the other technologies. So homomorphic encryption takes a seat at the table, right? And how to orchestrate that with other technology and what is the impact? Actually, it's difficult to foresee in this moment, except in a few instances. Like, for example, like Professor Xiong was saying, when you use homomorphic encryption in combination with differential privacy, and Kurt was alluding to this as well. That answer your question.
Thank you. So for my question to Abel is, if you were starting all over again, would you would use homomorphic encryption for your PPRL instead?
No, I think they're quite different. So we see a lot of the PETs as different tools in a toolbox. And so my view of it is that the PPRL function is record linkage focused. The homomorphic encryption, I think, is more maybe on the analytic side. And then you have federated learning, which is really on the learning side with machine learning models. And so we see each of them as having their own place. I would argue that there's now, in addition to PPRL, there's private set intersection algorithms out there, which are actually very effective that can be woven into this. And then on top of all that, then there's differential privacy and how do you present this in a way that is understandable to people so they can make decisions about it. So at this time, we're sort of betting on some combination of PPRL, like private set intersection with zero knowledge proofs, and then some combination of MPC, maybe, and FHE. So probably similar to the winning teams that Dr. Lee pointed out. It's going to probably look something like that, depending on the use case.
I still don't quite understand the advantage of PPRL when you could do homomorphic encryption with secure multi-party computation.
Well, what we find is that you still need to be able to identify and verify the same person across different institutions. That's where that layer comes in. And so even in our applications, we would bake in PPRL under the hood and then layer on top of the MPC.
I thought MPC can be one way to implement, to realize PPRL, no?
It's still, you need to have an algorithm underneath the hood that allows you to verify identity features. And so that's where the private set intersection stuff, the algorithms that we're using or trying to use now, would help with that part. The
right.
PPRL
Isn't private intersection considered one type of MPC?
I mean, I'm not sure if that's not how we've been seeing it, but we've been sort of taking that as a separate step, pre-step before the computation over that.
So I mean, you can't with fully homomorphic encryption, you can't hash the data. You can't hash identities.
No, you absolutely could, but one of the issues is still you have to find ways to verify it's the same person across, and so there is some key management that has to be done appropriately. So it's just an algorithmic step that has to be done under the hood.
But I mean, having listened to Jean-Pierre Houbeau, it sounds like he was able to do this with secure multi-party computation, right? To hash across records.
I'm not sure, but maybe they can comment on that aspect of identifying the same person.
So, Ro or Lee, do you have any comment to this?
Yeah, my understanding is MPC or fully homomorphic encryption are the different ways or different mechanisms that can be used to implement PPRL. To me, PPRL is one application of MPC. Essentially, you want to link individuals using secure techniques without disclosing the identity or disclosing the attributes.
And pretty much I had the same comment as Professor Xiong, right? So those are building blocks that I don't want to say they are completely interchangeable in the sense that the goal so for example, in private set instances of private set intersection, homomorphic encryption provides a very elegant solution to it. Okay, and it's also relatively efficient. It's been demonstrated multiple times. You can do the same thing with secure multi-party computation, as well as I would say private privacy-preserving machine learning. Right in 2000, I believe in 19, we had something. It was very interesting, a presentation that Abel was giving, where he was talking about the EMP toolkit. We actually released the framework, which is still open source, which is a very optimized library to do artificial neural network with NPCs, inference with NPCs, and underneath there was EMP toolkit to do all of it. Today we do all of these with homomorphic encryptions. There are differences in the way you actually harness the infrastructure that makes homomorphic encryption versus another tool more attractive, right? And one thing that I would like to say here is that homomorphic encryption in particular, I'm not married to any of these techniques, okay? It's that homomorphic encryption is sufficiently of a big of a problem for a research lab that is very interesting for an industry researcher to address. But with that being said, there is something that is very attractive about homomorphic encryption. If you look at the data life cycle into some use cases, so all the various stages and infrastructure and relay of data. So whether you do homomorphic encryption or you do not do homomorphic encryption, the data life cycle remains exactly the same. And so what happens to you is that the data valuation, when you actually draw insight from the data, either remains the same, or you actually starting drawing insights from data that before you could not touch. So which means that you are enabling new revenue streams. If you want to do the same thing, for example, with two-party computation, right? Now you have that the data life cycle changes, and there are new actors that it's not clear whether, I don't know, they get a discount for the insights that they are drawing because they are putting their own resources in, and other things. So the infrastructure impact is completely different, but the goal that you are achieving is the same. Okay.
Okay.
Other than that, I'm completely aligned with what Professor Xiong said.
Heidi.
Yeah, all three talks were fantastic. So Li-Xiong, I have a couple questions for you. So I loved your slide showing the combination of privacy technologies that were brought to bear in the UK-US privacy challenge. But you also commented that as a challenge, how do you communicate these technologies to stakeholders? And I wondered if all three of you have additional thoughts on how to communicate, and because it becomes a systems issue, depending on the problem, you craft a solution, you might be pulling, different techniques that have different strengths and combining them in ways that are really driven by the use case. How does one convey this to other people that won't have the technical knowledge, but need to be involved in the process, need to be involved in helping to bring these solutions forward?
Yeah, I can start from my perspectives and experiences, especially focusing on kind of differential privacy. And then I think Abel and Ro can comment more on these other use cases and encryption-based approaches. So in terms of differential privacy, Heidi, you're probably well aware of, there are a lot of discussions, both in the domain scientist community and also in the data privacy community in terms of how to democratize this technology, how to communicate this technology, how to, most central question is how to communicate this epsilon to the end users, to the stakeholders. So there are, I think people have made several progress in several directions. One is basically communicating this epsilon from both utility and privacy perspective, not in an abstract way, but giving more evidence, giving more concrete kind of outcomes. For example, from utility point of view, people have proposed ways of visualizing the trade-off in terms of utility and privacy. Given certain user functions, here is what you will get in terms of different epsilon values. Then people can make, or end users can make more well-informed decisions, choices. And in terms of privacy also, epsilon by itself is very abstract. It doesn't mean much to the end users. So people have proposed using benchmark attacks. I can essentially show you, given this epsilon, here's your re-identification risk. Here's your membership inference risk. Here's your data extraction risk. Then people can actually take a risk-driven approach to make, again, better informed choices. So these are, I see, are the two kind of perspectives or directions people have been working on. And then there are also a lot of other interesting issues in terms of incentives. How to incentivize people to share the data? And then you can also mix this in with other incentive mechanisms. You can even make payments, for example, compensations for user or for patients to exchange their data. And then there are a lot of game theoretic approaches that are looking into economic approaches, look into how to kind of associate the value with individual piece of data and then give proper and fair compensations, kind of in exchange of their privacy loss and their value they bring to the models, to whatever functions we are interested in.
That's fascinating and highly relevant. Can you just maybe throw a few references in the chat or follow up with an email? I'd love to kind of get a sense of who's working in that field of assigning value, methods to assign value, and any sort of work that's been done on potential compensation or how to credit that value, because that has a lot of an important larger context in terms of international data sharing.
Right.
Countries or places that have been that their incentive to share data is like, well, why would we share our data when you're just going to come in and reap the benefits and nothing will come back to us? Kind of like data colonialism. So these are things that we think and talk about a lot. And I'd love to just get a better picture of that field.
Yeah, for sure. I'll paste a few links.
Okay.
So I have a question more about sort of informed consent when it comes to, say, Medicare or CMS data. I don't know if people have actually consented to have their data used. I don't know the process. And if you combine it with other data, eventually you could probably, even if you had encrypted the data, you might be in reveal the individual. So I can see your privacy, differential privacy really help there. So how do you address that particular question of, when people haven't given informed consent, but the data is being used? I mean,
yeah. So I think there's a combined question of sometimes we have the consent, and then as exactly what you pointed out, later on, maybe there are some other new data sources that are made available, either de-identified or whatever aggregated form. And then that actually increases the re-identification or potential risk, inference risk of these individuals who have previously consented without knowing these potential future risks, right? So I think that brings a very interesting question. How do we actually dynamically revisit these consents? And maybe we need to kind of give these patients new information. Okay, now your risk has been higher. Do you still consent your data to be used? So that could be one thing. I think also this is related to the GDPR, kind of the data to be forgotten, right? So you have already consented your data, but then now we realize your risk is high. So can I actually request my data to be removed from these studies, from these models, and so on? So the patients should have the rights to do that. And then we should have the corresponding technology to support that, both in terms of governance procedures and also the computation, the technology.
So it sounds like every time you sign that HIPAA form, there should be an informed consent that people agree to.
That's right. Yeah, there needs to be a fine print also, or maybe I guess a better way is the consent should have an expiration date. Maybe that's an easier solution.
It's true that right now we don't have like that protection in place, but the other thing that would have to go along with that would be appropriate technical protections on top of that too. Because right now it's just by like the agreement itself, and our ability to actually execute on top of that, like protections, is still limited. You know, so you don't want to have people consent to something, but then you as an institution can't make it happen.
But every time you go on the internet, you sort of consent to your data being used, in a sense, right?
Yeah.
And you're not being asked for consent.
That's the unfortunate current state, it seems, today. So there's definitely room for improvement there.
And this seems like a larger problem in terms of law, but
Yeah.
certainly something at a local level for NIH research or any other research, scientific agency or medical agency can require in terms of funding.
Right.
Mhm.
Anybody have any other questions? Comments? All right, thank you very much for great presentations. And
Jonathan, Heidi, I'll send you the links since we run out of time. I'll send you links by email.
Great, thanks so much.
and I look forward to some of you being in person at September 6th. And if you have suggestions for the outline or for the agenda, let me know. Thanks.
Great. Thanks, Jonathan.
Looking forward to it.
Bye.